Dear colleagues, we are very happy to present at this occasion in showing the first results of archaeometric analyses conducted on pottery sherds from the northeastern Congo Basin. The study area, which I will show a map of on the next slide, has only recently been the subject of archaeological research. The first expedition in 2010 yielded multiple exciting sites. Pit features contained deposits of multiple often intact vessels. The sequence of ceramic groups consisted of three main phases. The earliest phase starts somewhat in the 3rd century BCE. They're all ovoid vessels, number 1 to 3 on the right, decorated by means of incisions and impressions, often with a comb, are replaced around the turn of time by the middle phase. The subspherical vessels of this phase, 4 to 7 on the right, are considerably bigger and show very diagnostic carinated rims. The late phase can be differentiated into at least 3 styles: Ilambi, Yakela, and Nkomba. Common among the Ilambi and Yakela styles is roulette decoration and pestle depressions, indicating that they were made by pounding in a concave mold. This is a very striking change to the pottery of the early and middle phase, which were made by drawing of a ring. We decided to subject this collection to further archaeometric analyses to investigate the variability of clay sourcing and preparation recipes. The study area goes from Engelenge at the mouth of the Itimbiri River in the west to Baombi 2 near the mouth of the Lindi River and near Kisangani in the east. The distance between these two sites is more than 300 kilometers as the crow flies. As you can see, not every site yielded samples from all periods, but some sites cover multiple phases. While we have many samples from the early phase from Bomani Yangwa, Ilambi Moke offers samples from 3 different phases. Important in our research is the geology of the region, which you can see here represented as different colors. Important is that further to the northeast, older pre-Cambrian rocks are exposed, while the Congo Basin itself is covered with younger sediments. The circles on the right show potential catchment areas around each site. The outer circle is 10 km from the site, while the dashed lines show 3 and 7 km distances from the site. Ian Whitbread and Olivier Gosselin and Alexander Livingston Smith give these distances as reference values for how far potters travel to obtain their resources. All following results are based on petrographic and geochemical analyses. Petrography is based on the study of thin sections made on the sampled sherds. These, only 30 micrometer thick sections, were inspected under a petrographic microscope in plane and cross-polarized light. The chemical composition of the sherds was investigated using a handheld XRF device. One goal of our research is to deduce the origin or provenance of the sampled sherds. As you are well aware, while we know about the place a ceramic vessel was put into the ground, this must certainly not be the place it was produced at. One distinct marker I was looking out for are often small fragments of plutonic, volcanic, and metamorphic rocks. These already give an idea to deduce the potential sourcing area for the used clays. Here you can see some examples. What is intriguing is that, as you saw on the geological map earlier, rocks of that general type are to be found to the east of the study area near Kisangani. All findings, on the other hand, are from further west. Thus, we must further review how these features can be used to provenance the clay sources. Unfortunately, our sole clay sample is from Basoko, a riverine clay without any rock fragments. Another indicator for the used clay sources are fragments of the silcious skeletons of freshwater sponges. These so-called sponge spicules appear as elongated isotropic rods in plain polarized light. Finding them tells me the clay source must have been in a lacustrine or riverine environment. In all cases, I only found isolated spicules. They were often heavily fragmented. Specifics of the processing of clays can be drawn from another type of inclusion. Most notable are grog particles, so ground up pieces of old pottery. Here you see some examples. The left set of photos shows a thin section from a potsherd from Bomani-Yangwa, where grog inclusions are present in all studied samples, but only in limited amounts in each of the samples. An outlier is a sherd from Ilambi Moke, you can see it on the right, which was produced from an iron-rich clay. Hence, the photomicrographs are nearly opaque. It contains lots of grog as well. As you can see from the figure on the left, grog tempering was only observed during the early phases. The view under the microscope offers a unique insight into the building blocks of pottery vessels. One can see different types of rocks and minerals. Rock fragments include pieces of granite, like you can see on the upper right, or little pieces of volcanic and metamorphic rocks, like I showed you earlier. The most abundant mineral is quartz, you can see an example on the lower left, while brightly colored micas are easy to spot, like the blue piece on the lower right. Also, fragments of an organic origin, such as charred plant remains, you can see one on the right, or phytoliths like on the top left, can also be seen. Also of importance is the degree of roundedness. As you can see in the lower left, chunks of superangular quartz are unlikely to have been deposited naturally. They are indicative of the potter preparing a mineral as temper agent. But the main question at this stage is how to make sense of all this information. For that reason, I coupled a qualitative approach with multivariate statistics by building on a paper by Cow et al. From the early 2000s. I recorded expressions of prominent features in a table and run a multiple correspondence analysis, an MCA. The results from that show the multivariate structure encoded in my dataset reduced to a two-dimensional space. While this method is standard in many fields, it is rarely used within ceramic petrography. The plot on the left shows the samples colored by their phase or style. The loading plot on the right shows the individual expressions of features in correspondence to the biplot of the left. For example, it clearly shows that sample YFG 79 on the top of the plot is clearly defined by metamorphic rock fragments being present. MOK 67 on the bottom shows lots of organic matter. Another extreme is MOK 70 on the right, which shows lots of grogs, again grounded old pottery being mixed into the paste as temper. Visualizing data like this is highly valuable when refining observations further and looking for clear patterns. These patterns can be further refined by subjecting the results of the MCA to a hierarchical clustering on the main principal components. I use the first 5 eigenvectors for this. The suggested clusters or groupings can be seen on the left. The observable overlapping means that the samples differ in dimensions higher than the 2 main ones plotted here. Also, very informative is the output on the right, which shows a statistically significant description of each cluster on the level of its feature. The percentages indicate how many samples showing a feature ending up in a given cluster, how many samples in a cluster show a given feature, and how many samples in the entire dataset show this feature. Just as an example on how to read this, in cluster 2, 100% of samples with clay pellets ended up in that cluster. Among the samples in that cluster, 66% showed clay pellets, while only 7% in the entire dataset showed that feature. I think it's pretty clear how, if you start understanding this kind of output, it will help further understanding any patterns in the recorded data. As the first main result, the analysis thus far provides 6 main petrofabrics. Petrofabric 1 is defined by large quantities of quartz, sandstone fragments, as well as charred plant matter and limited grog. It is associated with the pottery of the early phase exclusively. The second petrofabric is similar to the first, but lacks the charred plant matter. This fabric is only found in samples dating into the middle phase. The third petrofabric is also similar, but samples contain significant quantities of micas as well. Characterized by various kinds of plutonic, volcanic, and metamorphic rock fragments as petrofabric 4, it is only found among samples of the late phase. Similar to fabric 4, with significant mica component, but lacking the plutonic, volcanic, and metamorphic rock fragments, is fabric 5. As fabric 4, fabric 5 is restricted to younger pottery. The relative big pieces of micas were already visible on the hand specimens with the naked eye. The sixth and final petrofabric is characterized by grog. Again, it is restricted to the early and middle phase alone. As mentioned earlier, the second line of reasoning involved a geochemical probing of the scherds using a handheld XRF device. The device is mounted underneath the lead-lined sample chamber in the photo on the left. I choose to take 3 measurements per sample, each lasting 60 seconds. The resulting reports, an example of which you can see in the middle, were tabulated and a reasonable subset of diagnostic chemical elements was selected. As you can see on the right, inspecting these elements' correlations can already be quite informative, but this view lacks the correlation between all the measured elements. The basis for a substantial part of the interpretation is to run a principal component analysis on the subsetted list of chemical elements. The main plot shows the samples from the study area as colored symbols with a shape representing the individual sites and the color the phase or style. The gray dots show other samples from other parts of the Congo Basin that I measured as well. The so-called loading plot on the left shows which element is mostly present in which quadrant. As you can see, the samples from the study area are characterized by higher amounts of iron and potassium and lower concentrations of aluminium and titan than those in other parts of the Congo Basin. Among the samples from the Kisangani region, a few groups are already visible. Yakela scherds group somewhere together on the lower left edge of the plot, together with middle phase samples from Ilambi Moke. The early phase scherds from Bomani-Yangwa constitute their own group. I also ran the same clustering algorithm on the chemical data as the one I used for the petrofabrics and got 3 clusters out. You can already see some patterns such as cluster 2 in green containing the bulk of samples from Bomani-Yangwa. Zooming in on this specific site and a very distinct feature, a pit excavated at Bomani-Yangwa contained many pottery fragments and complete vessels that were sometimes stacked into one another. This feature can easily be compared to deposits of ceramic pots in pits known from the inner and western Congo Basin. Our question for this feature was if all these vessels originate from the same site or if the inventory is an amalgamation of multiple sources. In the PCA plot, you will see that I only used the samples from the study area this time. Highlighted are the samples from the pit in question. As you can see, these samples are not grouping together, indicating that it is not a cohesive and local inventory that has been deposited in this pit. However, with the colors separating different stylistic features, there is no clear pattern of certain features going together. We will certainly have to invest more time to understand the situation. Having shown you 2 lines of reasoning independently of one another, in this second to last slide, I want to bring all available information together, again making use of multivariate statistics. In blue, you can see the individual samples, while in red, their petrofabrics and chemical groups are displayed. The green text shows supplementary data that are not used during the calculations, but as a reference in the plot. As you can see, there are 2 strong main groups, with one set of outliers. The group on the left of the plot comprises all samples pertaining to the late phase. This group is characterized by petrofabrics 3, 4, and 5, the petrofabrics with large quantities of mica. The other group, the older pottery, comprises petrofabrics 1 and 2. The outliers on the top of the plot are the grog-tempered scherds from Ilambi Moke that also constitute their own chemical group. This shows us that there is quite striking distinction between vessels from the early and middle phase on one side and the younger vessels on the other side. In an attempt of a brief synthesis, I want to broaden the scope and embed the preliminary results from the northeastern Congo Basin into the outcome of my research in other parts of the Congo Basin. The divide between the early and middle phase of pottery on one side and the late phase on the other side indicates a shift in clay sourcing and preparation strategies that is also present in other parts of the Congo Basin. Most striking is this pattern along the Sangha River. There, potters during the early Iron Age used only river clays super rich in sponge spicules. New types of ceramics that arrived after the 10th century CE are not potted using these clays anymore. Among them, not one sample contained any sponge spicules. Thus, I think potters must have used an up to now unknown terrestrial clay source. On the other hand, along the Likwala-Ozerbe River, the use of river clays with their characteristic sponge spicules remained the norm even into modern times. There, sherds from the early Iron Age and those from modern times are nearly indistinguishable in terms of their petrography. The knowledge about the usability of clay sources also remained in the inner Congo Basin. In conclusion, the ceramics of the Congo Basin are a vibrant mirror of the persistence of knowledge among potters' genealogies of practice, as much as they illustrate change and flux among these communities. The research presented here can only be seen as a further step to unravel the great history of communities living in the Congo rainforest for thousands of years and their adaptation to a rich landscape. And with that, I thank you very much.